This is Sir Reginald Blomfield. He was a classical architect and garden designer, and staunchly anti-modernist. He is known for works including the redesign of Regent Street in London, various country houses and gardens, and pylons. Well, he gave us the word pylon anyway, named after ancient Egyptian architecture. As you can see, they look nothing like each other. This was when the Central Electricity Board was formed, tasked with beginning the national grid, to connect together the early local electricity networks into a national system. Blomfield was reaching the end of his career, and the government needed someone to lend some aesthetic credibility to power lines to smooth over opposition. A competition was held for the design of what were then called grid towers. Blomfield selected an entry from Millikan Brothers, an American steelwork firm. They were constructed of steel latticework in a three-dimensional truss. Blomfield justified the lattice design aesthetically as allowing a view of the sky through the towers, but this was nothing new, and was already the go-to design for electrical and other large towers worldwide. Quickly, tens of thousands were built across Britain, starting in Scotland. Building them from lengths of angle-section steel bolted together means they could easily be put up in the middle of nowhere without much heavy equipment. If necessary, all the pieces can be carried and directed by hand. Unusually, these first pylons, later known as PL1s, came in single or double circuit versions, one circuit being a set of 3 conductors, with the grid being 3-phase thanks to Nikola Tesla. Strings of ceramic insulator discs attach the high voltage conductors to the towers. Where the conductor changes direction or ends, the insulator is near horizontal, under the tension of the conductor. Hanging loops of jumper cable connect the different sections. Because of this sideways force, stronger deviation towers are required at corners, with several different sizes of pylon used depending on the angle of the corner. The biggest, terminal towers, are at the ends of the line. Looking again at the insulators, at the ends you can see arcing horns pointing towards each other. If, for example, lightning strikes a power line, the extremely high voltage can flash over the insulators, potentially causing a sustained arc which would destroy them. The shape of the arcing horns makes any arc blow itself out. For protection against lightning, power lines also have at least one ground wire at the top, which helps to shield the conductors. You can also see Stockbridge dampers, a type of tuned mass damper. This is to prevent resonance building up in the cables in wind. These early power lines run at 132 kilovolts. This is a 3-phase voltage, so for comparison purposes the normal UK mains voltage in your house is 400 volts, so these power lines are around 330 times normal domestic voltage. At this point in the video I was going to tell you how much power one of these lines can carry. I have spent the past year trying to research this, including poring over electrical textbooks and asking actual grid engineers, and frankly I'm tired of rewriting this script. Unfortunately the answer is it depends on lots of things which I'll get to later in the video. So purely to get this video done, my best answer is up to a couple of 100 megawatts per 3-phase circuit of 3 conductors. That's enough for about 100,000 kettles or a small city of a couple of 100,000 people. During the Second World War it was very useful to shift lots of electricity around the country, and afterwards large new power stations started to be built completely outside cities, where there was land available and closer to the coal mines. More power transmission capacity was needed, so from the 1950s bigger power lines were built as a supergrid. These pylons, known as L2, are very common indeed. This house has one in its front garden. These lines originally ran at 275 kilovolts, but many were later upgraded to 400 kilovolts, or about 1,000 times domestic voltage. Because of the higher voltages, the insulator strings are longer, with more discs. They also have twin conductor cables for more current capacity. According to my best information, at 400 kV these can handle up to about 1500 megawatts per circuit of 3 conductors. By the 1960s even more power was needed, so the CEGB started building the biggest common pylons in the UK, L6. These are also very common and include these pylons along the M6 through North Birmingham. They return to having arms of different lengths, instead of having the conductors stacked vertically. This helps prevent the different phase conductors clashing with each other if they sway in the wind. L6s can, and usually do, carry quad cables at 275 or 400 kilovolts, giving roughly double the maximum power capacity of an L2 line. According to estimates in current National Grid planning documents, these are good for about 3,000 megawatts per circuit, and a pylon carries 2 circuits, so a single line of pylons could, in a pinch, transmit electricity to most of London. Now it's time to discuss the things that affect the capacity of a power line. So electric current passing through resistance like a cable produces heat. Too much heat weakens the cables and also makes them expand and sag. How much they can be allowed to sag depends on their height above the ground, what if anything is underneath the cables. The sag also depends on how high and how far apart the pylons are. How much the cables heat up depends on the climate. The same power line at the same voltage can carry more power in the Arctic than in the tropics. For the same reason, a power line has higher capacity in winter than in summer. The longer a power line is, the more power will be lost as heat, and the less will get to the other end of the line. Power factor is another complication. In alternating current circuits like the grid, many types of load draw more current than they actually use, and this reactive power heats the cables up without achieving anything. Almost all power lines form part of a network, so the power that wants or needs to flow through any particular line depends on all the other lines, and you don't really want any power line to be running at capacity. You need to be able to switch them off to do maintenance or if something goes wrong without having a massive blackout. So the capacity of a power line is very complicated, and all the figures I've given are rough maximums. Britain built a lot of spare power line capacity in the 20th century, despite this being controversial at the time, and this has served us well in the time since. But electricity generation continues to evolve. The large regional coal-fired power stations have closed down and have been replaced by gas and wind power located further away from demand. As well as this, transport and heating are switching to electricity. All this puts more strain on the grid and creates the need for new power lines. Putting 400 kV power lines underground is a real pain for various engineering reasons, and is extremely expensive because of that, 5 to 10 times the cost of overhead lines, and this cost comes from people's electricity bills. So the National Grid set up a competition to find a new, more popular design of pylon. They chose this, the T-pylon, designed by Danish firm Bystrup. It's tubular rather than a lattice. This isn't a new idea. Here are some old 132 kV tubular pylons in Castle Bromwich. They're not unusual in urban areas around the world. These T-pylons are being built for a new 400 kV power line across rural Somerset to better connect the under construction Hinkley Point C nuclear power station with the rest of the grid. Elsewhere, when pylons are moved or replaced like this one was for HS2, they tend to be with slightly lighter variations of the standard lattice designs. With electricity generation continuing to change and spread further away from the cities where most electricity is used, we will probably need even more pylons in the future. Is it time to embrace the pylon and recognise how they make the electrification of the world possible? Let me know in the comments. If you enjoyed this video, please do consider subscribing or clicking one of the other buttons. I've been Martina, and thank you for looking at things with me.